All right. Welcome back to this is chapter 1 and part 2. And this is slide 16. Okay. And all right, so what we're going to be looking at here is we're going to be looking at units. So the specific units that we're going to be using. And in science, we use the metric system. Some engineering places will use standard system, but in chemistry, we use metrics only. And in the engineering companies that I worked for semiconductors, we only used metric as well. So it's very good to be really like very comfortable with those things. Okay, so let's take a look at what we've got going on here. And here what we do is we have the property, okay, and the unit that goes with that. So if we're talking about mass, the base unit is the gram. If we're talking about time, the base unit is the second. If we're talking about distance or length, the base unit is the meter. Volume is done in liters. Temperatures in kelvins. Okay, and that's we'll use kelvins, but sometimes we'll also use degrees Celsius or Celsius like this. And some things require it to be in Kelvin, and some things you can use it in Celsius. We will not be using Fahrenheit. When we're talking about number of particles, we're talking about the mole, sometimes abbreviated MOL. And energy is going to be the joule. Sometimes we'll also talk about calories as well. And those are both units of measure. Okay, so the base unit always designates the type of quantity being measured. And the SI units are based on the units of science. Okay, now some of these, a mole is mole, gram is gram, but a joule is a derived unit or a combination of them. And so what a joule actually is, it's a kilogram meter squared per second squared. Okay, and that ends up being pretty important when we're talking about speed of gases, when we're talking about root mean square velocity, but also when we're talking about some other places. We'll use joules when we're talking about energy as well. All right, now we are into slide 17. And there's different ways of showing the metric system. All of these base unit, all of these that I have listed here are smaller than the base unit. Okay. And here what I've done is I have just used grams for these, but you can put in any of these meters, liters, seconds. Okay. So for example, this could be 10 decimeters in 1 meter. Okay. This could be 100 centimeters in 1 meter. This could be, instead of milligrams in 1 gram, this could be 1,000 milliliters in 1 liter. Okay. Here we've got micrograms, but it could be micrometers, microliters. Microliters are used a lot in biotech. Okay. Here you've got 1 times 10 to the 9th nanograms in 1 gram. But more commonly, we're going to use this in light. So this would be 1 times 10 to the 9th nanometers in 1 meter. So you can change any of these base units to match. Okay. And let's talk about how we're going to convert these. So I'm going to stop sharing this for a moment. Hello. And we're going to open a whiteboard. Okay. And hello. Okay. So, all right. So hopefully you can all see my whiteboard here. And there we go. Okay. Now, let's take a look at how we're going to convert a couple of these. And a really great thing to do now, whenever I flip to the whiteboard like this, is to pause the video and try to do the work on your own. If we were in class, I would be like setting it up and then making you calculate through it. So every time you're watching this, pause the video and get out your calculator and do this yourself. Okay. Because, and I always tell students, this is about doing, it's about learning and participating. Chemistry, science, engineering, they're not like an audiobook. So don't listen to this video. Make sure that you're filling in this notes template and grabbing a calculator for all of these math sections. Okay, so when we're taking a look here, our first one on this list is 945 picograms to grams. Now, if you take a look at what you have above, you'll see that the unit says that there are 1 times 10 to the 12 picograms in 1 gram. Okay, so that is taken from the slide that I just showed, so you should be able to find it in there. It was line number 6. Okay, and now what we're going to do is we set this up. And so we start with our given right here, 945 picograms. And you can put that over 1 if you want to. And then we set up a conversion, and we have picograms on the top. So we have to put picograms on the bottom and grams on the top. And now we put in this exact conversion. So that becomes 1 here and 1 times 10 to the 12th down here. Now, everybody's scientific calculator is a little bit different. And I want you to work this with me. Because if it's not coming out correctly, then you need to contact me by email or see me in class, and I will help you figure out exactly how to put scientific notation into your calculator. Again, every calculator is a little bit different. And my experience is that when students come in, about 75% of them are putting scientific notation into their calculator incorrectly. This is going to highlight that. So please make sure that you pause the video and work this through on your calculator. Okay, so what you're going to be doing with this is 945 divided by 1 times 10 to the 12th. Now on your calculator, it's my calculator has a 1 and then a times 10 to the button and 12. Some calculators are going to be 1 and then second EE 12. Some calculators are going to be 1 and then an EXP 12, and it just depends on what you have. Okay, again, if you're working this and you don't get what I get, then please make sure that you let me know. All right, and so this becomes 9.45 times 10 to the negative 10th, and your units are grams. And that's how you know that you are done. You need correct units as well. All right, let's work another one. The next one here is 459 nanometers, 2 meters. Okay, and from line number 5 in your chart above, you'll see that you have 1 times 10 to the 9th nanometers is equal to 1 meter. And again, we've changed our base unit here. And so we can set up our given value here, 459 nanometers, and we can put that over 1. And then we set up our conversion. We have nanometers on the top, so we put nanometers on the bottom and meters on the top, and that's so that we can cancel these out, okay, like that. And then we're just left with our meters. And now we have to put this in, 1 times 10 to the 9th and 1. Okay. And again, this means 459 divided by 1 times 10 to the ninth. Okay. And your calculator, again, test this on your calculator so that you know that you're doing this correctly. I have seen many students, like they're taking notes, they don't pull out their calculator, they don't practice it, and then they don't know how to use their calculator on the test and they get these wrong. And I give very little partial credit on this. You have to be able to use your tools because you're going to be engineers. Okay, and you get 4.59 times 10 to the negative 7th meters. And that is your final answer. Ooh. Okay, hang on. Sorry. I accidentally, hang on. Here we are. We're back. Sorry about that. Okay. And here we are, and we are, yep, and we are, I keep accident. There we go. And we are here. And so here we are, and we are complete. Okay. All right, excellent. And now let's take a look at the last one on here. And this one says that we have 1.25 liters, and we are going to convert that to milliliters. Now, from line number 3 in the chart above, it says that there are 1,000 milliliters in 1 liter. Okay, and so we can set this up here. Again, we start with our given 1.25 liters over 1. And because we have liters on the top, we need liters on the bottom here. And there we go with our milliliters. And now when we put this in, see the 1,000 milliliters, that 1,000 is going to go on the top and the 1 is going to go there. So whatever value is here is what you put here. Okay. And now we're doing 1.25 times 1,000. Okay. And this will give us 1,250 milliliters. And we are done. Okay, so hopefully you worked all these through on your calculator at home. That is very, very, very important to do. All right. And all right, so I'm going to go ahead and clear these, and we are going to sorry, go back to our slides. Okay, so now on this slide, what we're looking at is we're looking at working through something larger. Okay, and here we are. This is slide 18. Okay, and so we're looking at slide 18. And in this case, these are larger than our base unit. So again, you could put in meters, grams, liters, seconds for any of these. And an example for some of these might be, let's look at a few of them. So right here, we have 100 grams in a hectogram, 1,000 grams in a kilogram. You might also say here that there are 1,000 meters in 1 kilometer. Okay, that there are 1 times 10 to the 12th, let's see, liters in 1 teraliter. You can put anything in here that you want to. Okay, these aren't we don't use quite as many of these really big ones when we're working in chemistry. Usually we're working with smaller than the base unit because we're talking about atoms. Okay, So again, let's go ahead and work on, I'm going to pause this and we are going to go back to that whiteboard. Okay. And we're going to work some problems again. All right, so with this one, let's take a look at a couple of examples here. And this is very similar to what we were doing before. And we have 296 grams, and we're going to convert that to kilograms. Okay, so if we look above, this is line number 3 from above, and it says that there are 1,000 grams in 1 kilogram. Okay, so we can set up our conversion with 296 grams, and we can put that over 1. And now our grams are here and our kilograms are here. And we can see that the 1 goes in front of the kilogram and the 1,000 goes here. Okay. And the way this is set up, we're actually doing 296 divided by 1,000. And when we do that, we get 0.296 kilograms. Okay. So similar to what we were working with before. Now, our next one here is a bit different. So let's take a look at what we're doing here. We are going to be combining 2 things. So it says 4.98 kilometers, 2 millimeters. Now, notice from above that we don't have a unit that goes from kilometers to millimeters. So if you're really comfortable with the metric system, you might already be able to do this kind of in your head. But I'm going to show it for those that aren't real familiar with the metric system. And so we're going to use 2 different conversions. And the first one is from slide 17. We can see that there are 1,000 millimeters in 1 meter. And from slide 18, okay, and you can see that on your chart. On slide 18, we can see that there are 1,000 meters in 1 kilometer. So we can set this up like so. And we start first with our given 4.98 kilometers, and we can put that over 1. And now we're going to use this conversion, and we put kilometers on the bottom because it was on the top here, and meters on the top because that's what we're going to. And so the 1,000 goes here in front of the meters and the 1 into the kilometers, just like in our conversion. And then what we're going to do is we're going to use this second conversion here. And we need we've got meters on the top, so we need to put the meters on the bottom here, and then millimeters on the top. And so from this, we can see that there are 1,000 millimeters in 1 meter. Doing this on our calculator, we have 4.98 times 1,000 times 1,000. Okay. What we will get out of that is 4.98 times 10 to the 6th millimeters. So again, work through this and put those calculations up there yourselves as well. All right. Let's come away from our whiteboard now, and we'll go back to our PowerPoint. Okay. All right. So here we are. This was slide 18. Okay. So let's come down and look at temperature. Okay, so here's some examples of, you can see the temperature. Sometimes people will use 9/5 or 5/9. If you know enough about math, you'll know that times 9/5. 9/5 is 1.8. And 5/9 would mean divided by 9/5 or divided by 1.8. And I've basically changed the 9/5 to 1.8 because it's just easier to put into your calculator. And you'll see that quite often as well. Okay, so here you're showing where all of these are. You have your conversion here. So here you have your Fahrenheit temperature and your Celsius temperature scale and your Kelvin temperature scale. And Kelvin is adjusted so that basically there are no negative values in that. So negative 273.15 degrees Celsius is 0 Kelvin, or absolute zero. Okay, and that's why we are going to use these. And here are your conversions. Okay, so make sure that you are writing these down on your notes template. You're going to need them. It says a place for equations, and you're going to put these there. All right, so let's do some practice. Hang on. Practice isn't here. I'm going to need to go back to the whiteboard for that. All right. All right, here we are back at our whiteboard, and let's take a look at these. So the first one that I have here is we're going to be basically converting. So convert 19.3 degrees Fahrenheit to Celsius and Kelvin. All right. Now, an important thing here is you're going to need to do these. Remember, you get a cheat sheet for all of your tests. But for my students, if you take a look at your page that you're given for tests, you can see mine right here. You're going to have this conversion sheet and a periodic table, and this will be available for all of your tests, and your temperature conversions are on there. So don't forget about that. All right, so first of all, in order to convert, we can't convert directly from Fahrenheit to Kelvin. So our step one here is to find our Celsius temperature, or find degrees Celsius. And when we're converting to Celsius, our equation for that is going to be degrees Fahrenheit minus 32 over 1.8. Okay, so let's do that math. Okay, so we have 19.3 minus 32 divided by 1.8. And again, you should be pausing and practicing this on your calculator. Your calculator is going to give you the value of negative 7.0555, et cetera, et cetera. All right, so we're going to go ahead and report this. We have 3 digits here, and we'll be talking about significant figures in a little while, but we're going to be reporting this with those 3 digits as well. So this will become negative 7.06 degrees Celsius. And that will be our final answer. So now let's take a look at our step 2 here, and finishing that up and finding our kelvins. So we'll find Kelvin, okay, by doing our degrees Celsius plus 273.15. And the adding and subtracting rules are a little different, so we'll be keeping all of the digits on this one. And when we work through this, we get 266 here, actually, let me come here. We have negative 7.06. Erase that. Negative 7.06 plus 273.15. I want to get ahead of myself there. And we get 266.09. And your units for that are kelvins. And because we're now using adding and subtracting rules for significant figures, we will keep all of the digits. All right, so that is a great lead in to significant figures are next. All right, so here we go. We are taking a look now at that Celsius, and there we go. All right. Okay, I just have to go back into it. It's a little tricky sometimes. There we go. Oh, sorry. What happened? There we go. All right, so back to our current slide. And just to check you up here, we are now on slide 20, and we'll be looking at significant figures. So here's slide 20. Now, significant figures are basically the digits reported that tell everybody how secure or how confident we are in what we're working with. Okay, so when we're talking about significant figures, basically any non-zero digit is always significant. So we'll go ahead and add that in. So non-zero is always significant. And then the rules change when we have a zero. Okay. So when the zero establishes the decimal place, it is not significant. So basically, these zeros are what we call trailing zeros, and they are not significant. And these zeros are leading zeros, and they are also not significant. So when we're working through this, these three are significant, and these two are significant. Okay. Now, when we do have a decimal point, then what we're looking at is that we are looking at it being significant. Okay. So here you have 3 significant figures, and here you have 4 significant figures. So let me show you a little bit more looking at this. All right. So in this first one here, we have this 800 right here. Okay. And then I have these 2 zeros, and these are ending zeros with no decimal point. So in 800, we have 1 significant figure. Now in this next one, 8, we just have the 1 digit. So this is also 1 significant figure. And remember up here that those leading zeros are not significant. So in this one, we also only have 1 significant figure. Okay, now here, and you see 808. And so this one has 3 significant figures. And here we have 0, and we have anything at the end. So because it follows the decimal point and everything else, then we have 1, 2, 3, 4, and this is 4 significant figures. So one of the things that you're going to need to be able to do is look at those sig figs. Okay. Okay, let's take a look now at scientific notation. Right, and I think that we'll do some scientific notation and some more sig figs, and then we'll take another break. I like to have the videos be a little shorter. Okay, so scientific notation is used to write very small or very large numbers. Okay, or not very small, very large. You can basically put any number into scientific notation. So when written in scientific notation, all the digits that we use will be significant. Okay, so let's take a look at how this works. So first of all, here we have, so again, remember to use this, this rule. So first of all, if I look at this first one, 56 million, I have 2 significant figures here. Okay. And now I need to put this into scientific notation. So what I'll do is I'll start right here and I'll say, this is what a decimal point is. And I'll count 1, 2, 3, 4, 5, 6, 7. And that means that in scientific notation, I have 5.6 times 10 to the 7th because it's greater than 0. All right, now let's take a look at the next one here. We have 302. So we have 1, 2, 3. I'm going to put the dots up above now. So this has 3 significant figures. Okay. And now I imagine that I have a decimal point here and I move it twice. And this becomes 3.02 times 10 to the 2 in scientific notation. Now, see this last one, we have a decimal point at the end already. That means that all 4 of these are significant because we have that decimal point. So this is 4 significant figures. And I need to keep them all when I go to scientific notation. So now I'm going to move the decimal point that's already there, 1, 2, 3. And this becomes 4.000 times 10 to the 3rd. And that's how we show all of our values in scientific notation. Okay, now let's take a look at this one here. And then maybe I'll practice a couple going the other way just so that you can kind of remember how that works. Okay, so here we have 1, 2, 3. So this has 3 significant figures. Okay, and now what we do is we take the decimal point and we're moving it in the other direction. Okay, so we have 1, 2, 3, 4, 5, 6, 7. And so this becomes 7.93 times 10 to the negative 7th. Okay. And now in this one, we just have this 1 here. So this has 1 significant figure. And then to convert it to scientific notation, we move this decimal point 1, 2, 3, 4, 5, 6. And we have 3 times 10 to the negative 6th. And now in this one, we have 1, 2, or 2 significant figures. And again, we're going to move that decimal point 1, 2, 3, 4 after the first digit. And this becomes 5.0 times 10 to the negative 4th. All right, so what I'm going to do is I'm now going to just show you a couple quick examples where we're working in the other direction. All right, so let's say that we have 1.23 times 10 to the 8th. Okay, that means that we have 1, and then you count 1, 2, 3, 4, 5, 6, 7, 8. And then I can put in commas, and I have 123 million. Now let's say that that was 1.23 times 10 to the negative 8. Okay, that means we're less than 1. So I start with 0 point, and then I count 7 zeros because this last value is going to be our last place. So I'll count 1, 2, 3, 4, 5, 6, 7, 8, and then 2, 3. Okay, so that's how we would convert those two from scientific notation back to standard notation. And we're keeping, in both of these cases, we have 3 significant figures. All right, now let's take a look at a couple more examples here. This is slide 22. Just for anybody that's taking a peek at what we're doing now. Okay, so for calculated values, the number of significant figures depends on whether you're adding or subtracting or multiplying or dividing. Okay, so for multiplication and division right here, The number of significant figures in the result must be the same as the number of significant figures in the factor with the fewest significant figures. So see how this one has 2 and this one has 4. That means that we can only have 2 in our final answer. Okay, so here we have, when we multiply these together, we will get 1109.04. But we can only have 2 significant figures. So when we report this, it has 1,100. Or 1.1 times 10 to the third in scientific notation. Now in this next one, okay, here we have 1, 2, 3. So we have 3 significant figures, but here we only have 1. Which means that we can only have 1 significant figure in our final value. Okay, so let's take a look at what we have here. When we multiply these together, and feel free to be multiplying these as well at the same time. When we multiply these together, what we get is 39,480,000. Okay. All right. Now this is the value we get, but we can only have 1 significant figure. So this becomes 40 million. Okay. Or 4 times 10 to the 7th. So make sure you don't just report this at 4. Sometimes people will leave off those zeros, and it's really important that you keep your magnitude correct. And you'll notice in this case that I rounded up. So in this case here, I took this value 1109 and the 0 rounded that down to 1100. But this 9, I could have this 9 here. The 9 rounds up. So 39,480 becomes 4. Okay. Now, bit different when we are setting up adding and subtracting, because this is determined by the position of the first uncertain digit. So what we mean is, if we take a look here, we have to line them up. 4.882 plus 0.3. Okay. Now, when we line those up, notice that our last digit happens right here. So we add these together and we get 5.182. The 8 rounds this up and our final answer is 5.2. Okay. Now let's take this one. This one's going to be a little bit different and it can be a little tricky to work through. So when we take a look at this one on the bottom here, okay, I'm going to rewrite this using standard notation. So I'm going to convert this to standard notation first. And so this becomes 1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I'll go ahead and put in my commas. Okay, and now 8 times 10 to the 8th. Let's start lining up here. I have 8 that I have to move it. So I have 1, 2, 3, 4, 5, 6, 7, 8, 7. Okay, so I've just converted those to scientific notation and I'm adding them together. All right, so now when I'm adding these together, let's go ahead and add them up. So I get, turn on my calculator. I actually haven't done this one yet, so let's work through this. I get 1.21 times 10 to the 9th. I'm going to leave it in scientific notation for this part just because it's easier on my calculator. 7.8 times 10 to the 8th. And I add it together and I get this value. I get 1,990,000,000. 0,0,0,0,0,0. Now, if you look at this, even though this one only has 2 significant figures here, this is where the significant figures end. Oops. accidentally went over that one. There we go. There. Okay, this is where those significant figures end. So I'm going to keep this whole value, okay? And so it becomes 1.99 times 10 to the ninth, okay? So even though there's only two significant figures here, I have three here. And it's all based on where that decimal point or where the last significant value lies. Okay. So let's take a look at some examples that we have here. This is our next slide, slide 23. Okay, so let's just practice these. So first of all, this first one, you can be practicing this too, or pause and practice it. We've got 4.3 times 0.31, and that would give us a value of 1.333. Okay, but when I look at this, I can only have two significant figures here and three here. Okay, which means that I can only have two in my final answer. So this 3 rounds you down to 1.3. Okay. Now I'm going to come over here. I've got this next one, and I have 4.033 plus 88.1. Okay. And now remember that this one's a little different. This is where my values end. So when I add these together, I get 92.133. And again, those threes round down. And so this becomes 92.1. Sort of circle my answers here. Now let's take a look at this one. We have a division bar here. For some of you, remember again, this one, make sure that you're practicing this last one on your calculator. Some calculators are just very different with the way they require this. Some even will require scientific notation to be in parentheses in the denominator. So if you have one of those calculators, make sure that you put that into parentheses in the denominator. Again, practice this. Let me know if you are not getting the same values that I am getting. That is super important. Oh, and so when you do 5.6 divided by 1.732 times 10 to the 4th, what we end up with here is, on my calculator, I have 3.23326. I'm not going to write it all, times 10 to the negative 4th. And we take a look now at our significant figures. And we can see that this one has 1, 2, 3, 4, but this one only has 1, 2, which means that this is how far we can go. And now it's, okay, I did not plan that, but all of these round down because we are less than 5. So we have 3.2 times 10 to the negative 4th for our final answer on that one. Okay, now let's just kind of go over a few things left over here. So when we're counting, and that's a big word here, counting discrete objects, the result has no ambiguity. And that means that it's exact and it has infinite significant figures. So 2 pennies is exactly 2 with an infinite number of significant figures. Also defined terms within a system. For example, 1,000 grams over 1 kilogram has infinite significant figures because it's exact. 12 inches in 1 foot has infinite significant figures because it's exact. The only unit between two systems that is not has significant that does have significant figures is our centimeters. So 2.54 centimeters is 1 inch exactly. But if we were to say that there are 1.609 kilometers in 1 mile, then this one would have 4 significant figures. Okay. All right. Now that is a great place. We're going to pause. That is the end of part 2, and we will come back for 24.